Chris here? Chris Lindler? Yeah. Okay, that's Chris. That's the final one you need. Shall we start? There you go. Amazing. There you go. So yeah. All right, welcome everybody to the last session. As opposed to a parallel session that we had yesterday, we'll do a more serial session. A few speakers in serial fashion. I will start off with doing a short introduction on Python for those who've never seen it before, what all the hype is about, maybe about 5 or 10 minutes. We'll do the same thing with IDL. We won't concentrate much on the visualization aspects yet, maybe show a plot, but the basic language so you get an idea what you can do with it. And then we'll go into a number of visualization aspects. Matt will talk about some Python applications. Anatoly will show some IDL widgets, which is very neat, a very powerful tool in IDL. And then we'll get to some specific applications. Derek has mentioned the beautiful stuff he does with POV-Ray. And Chris will talk about Visit that we hear about more later. So, and to focus ourselves, especially on visualization, I had a few things, but this is more meant for the speakers on visualization programs themselves. If they can concentrate on a few common things that you see there, programs are sometimes very specific to dealing only with grid or only data or both. Some of them can be driven by external programs like a client-server model. That's very useful if you're on a remote cluster and you can send data on a program that's on your workstation itself. Scripting, it's very useful if you have a program that can be scripted using Python or some other language. I happen to be an old fan of PartyView, which is sort of an interesting particle program. Can it also make animations like what Visit can do and GLNemo? They produce HD video straight out of the box, very useful. And then, of course, lastly, although that shouldn't be a showstopper for you, how easy is it to install these? I mean, Visit, for example, is one of the more complex ones, but because they are so complex, people have written very useful scripts that put it all together for you. And you can also download the binaries, of course. So, scripting. We've got lots of scripting languages, and we're only going to deal with 2 of them. And not all of what you see on the right-hand side is exactly true, but that just came out of my mind as I was listing a few of the popular ones. Some have the top one, Scheme, a very Lisp-like language. I don't know if that's true, but it is the language of parentheses. Perl, to me, when I write Perl code, a day later I've forgotten what it all means, and you can probably see why. TCL/TK was a very popular, powerful language with these square brackets that execute something and level it up to the next level, in some sense very similar to Scheme. Python we'll talk about today. Ruby is very similar to Python in my mind. The Ruby people always like to say it's the language of the least surprises. And CINT, often forgotten by many people, we've heard several times, is that C is perhaps the language that is best suited to deal with both extremes, too complex, object-oriented like C++, more powerful than Fortran, but Fortran is a little aging, well, unless you do Fortran 90. So it sits in the middle, and CINT is an interpreter built by CERN, another nice project come out of CERN. And in principle, if you write your scripts in CINT, they're actually like C programs. And once you've discovered, hey, this is a thing I do a lot, you just put it in a library and you're ready to go. You don't have to translate your 1,000 or million lines of Python code into an executable code just because Python became too slow. But it is, certainly in the astronomical community, not much used. IDL we'll get to, and here's my favorite MATLAB cryptic notation. So let's do a few minutes on Python then. What's all the hype about? I would say Python has been at least in our community, mostly forgotten until a few years ago at the bottom line when the scientific Python environment came about, which is capable of handling in a much better way numerical arrays that speed up some of your numerical computations, a very versatile plotting environment that will show. But other than that, it's open source, it's free. It's a Dutch product, so I'm proud of that. Interpreted and dynamic, and it's very important that you have a language that's dynamic, so you don't have to declare too many things. It's quick you don't have to compile, and so forth and so on. It's object-oriented. You can extend it, you can use it with other languages. Many libraries, and I've heard that several times that people talked about. One of the strong points of Python is that every conceivable library that you have, FFTW, GSL, FITS.io, they all have hooks into Python, so you can use them inside your Python scripts. And you have still the advantage of fast code in a particular library that's useful, and yet you can use this in a quick scripting language. So here's a couple of things about the language. Do I have a pointer for this? Yes. A few things. When I say the language is dynamic, if you declare x to be 1, then, well, that could be an integer, that could be a floating point number, you don't know. In fact, usually what happens in Python is that becomes an integer. But equally so, immediately after that, you could say x equals double quote 1, 2, 3, double quote end, and it becomes a string. So the old x has disappeared, a new x comes in. Now, we're all familiar with scalars, and then Python is very rich in a number of very useful data structures that you may or may not use. Certainly arrays or lists, as they're called, the notation is to use square brackets. And if you want an element, so here's an array X again that has 3 elements, 1, 2, and 3. And there happens to be an intrinsic function in Python called range, and this does exactly the same thing as that. Now, if you do things with parentheses, they're called tuples. And they don't have to be the same type. Here is numbers and here is strings. And the same thing as with an element from an array. If you square bracket an element, you extract an element out of that tuple. And in this case, because that guy was a string, I want it as a float, so you convert it to a floating point number. Dictionaries are also perhaps a little less used in Python, but they're named values by a keyword. You don't index them by a number, the ordinal number in a sequence, but by the value that is associated with, here's the keyword and here's the value. So if you can look up something by its keyword, apps, and what it will return is 0.05. And to distinguish them from the other ones, they put curly braces around it. There's lots of more things, and then once you have a list or a tuple, there's lots of things like how do you add new elements to it. You can sort lists and do all kinds of operations with them. And I won't go much into that. So that's the lots of built-in functions that operate on these things to do all kinds of useful things. And then in addition to that, there's a little bit of control flow that you need. You need to if then else kind of things. You loop a little bit, and there's some examples here. Here's the language of the slightly more surprises, I guess. The else or else if is now called elif, made a little shorter. But you also will see there's no use of parentheses here. And after the Boolean expression, there's a colon. And it so happens that Python uses an indentation to denote where the flow is. If you made a mistake in the indentation, either the Python interpreter will warn you for that or will get very confused. Usually if you use a syntax highlighting editor or a good editor that knows about Python, and the modern ones all do, they not only syntax highlight, they help you with the indentation. If you certainly want to do an if, end if type thing around the whole block, you tell Emacs or VI and it will boink, shift right the whole block or shift left, and you have the correct indentation. But unlike in C or in IDL, for example, there's no markers to tell you where the if and the else and the end if ends. Looping over a list. Say again? Well, if it would go on, it would go on, but I'm assuming that there is another statement here. So this would be the last one in the else.
Can you consider like I equals I plus 1 to the next
Yes. I have an example. Here is an example where you put the else on the same line. So there is no else here. There's only an if. So that's the one-liner. And the other useful things are things like functions. And that's done with the definition of a function. And here I've created a square root thing that is insensitive to the sign. You know, here's another one-liner. If x is less than null, you return math.square root of minus x. And this is an interesting thing that you see here. And Python is full of that. It is sensitive to a namespace. Normally what the user would have done is they would have set somewhere at the top, unlike the include statement in Fortran or C, you would import something. And you would say import math. And then suddenly you have all kinds of math functions and data structures available. And you would have to say math.square root, because somebody else may have written some function that takes a square root of a vector, which is not compatible with the square root of this number over here. Okay, so these are sort of the basic things that you would use. I'm going to skip that one. And to highlight this a little bit more, I wrote a little function last night called nbody. And here's an example of a function that reads a file. And let me just go over a couple of lines that tell you the kind of power that you have from this. You open the file and you return the file pointer. Then this file pointer is now an object, and it has a member function called readLines. And I'm just taking the default there because it returns a set of lines. So this thing lines is essentially a list of strings that could be 100 if there's 100 lines in the file. And I close the file quickly. I initialize some variables because I want to loop over and count. And as I loop over these lines, so in this loop, you'll get a variable called line, which is just one of the line out of this set of lines. Now, I want to know if the first character string is one of these magic markers. It's a comment, so you continue on. Then the line is split in pieces, and you can split based on tabs or spaces or colons or whatever you like, and the default happens to be spaces. So this thing, words, are essentially the pieces in the file that were separated by spaces. So if you have an ASCII table with, say, 6 columns, there'll be 6 elements in this thing called words. But there'll be ASCII strings. And so I do some more checks. And when you loop over the words, these guys are ASCII strings, and I want to convert them to a float and then append them to the row, which I initialized as a blank row before you started in the loop. So that's a very simple example how you quickly scan an ASCII file that represents a table, and you return a table as the object to the guy who called it. So those are useful functions. I won't go to do that one. The other thing that's very useful but slightly more advanced is when it becomes object-oriented and you define a class. A class is essentially an object. For example, in this case, we're creating a body, and the body has as elements in it how many particles there are in, the positions, the velocities, a few other things, whatever you can think of. And that's done in the initialization. This piece is essentially the same as I showed you before. You parse a little table and it sticks it in some private space. And then there is a member function defined that computes the forces in a straight and square algorithm over here. And one function that does a simple forward Euler step. And that's all you need. If you then, by the way, all of this will be in your material, so you can look at that later. And there's actually 3 versions of this I'll go over quickly. And what you do is that class called nbody is read from a file. So you now have this object called A that represents an nbody snapshot. And then by typing a.force with a certain softening, behind the scenes, all the forces have been computed. I want to print it on the screen. And then you step over n-step time steps, advancing the time first with an Euler, recomputing the forces so that the next loop we have the forward forces for Euler. And at the end of it, I just do a simple list. Very simple nbody code, straight programmed in Python. So I did that last night, and I compared it to some code that I have in Classic C, which ran in 0.9 seconds, a certain benchmark. And I actually was curious, and I decided to recompile that code and do it in single precision, because that version is in double precision. That actually ran slower. I remember in the old times it used to run faster, but not on these modern machines anymore, because you probably have offset registers and all of that stuff. So the version that you just saw, I ran in Python, classic so-called bad Python for numeric work, ran in 3.5 seconds. Oh, I said to myself, that's not bad. It's only 3-4 times slower. Then, and you can find that in the other material, I won't show it to you, but there is a way to use these numeric arrays that I mentioned, which are like an IDL whole array notation. You can type a vector v and you can do simple operations on the whole vector, yeah?
Did you use cycle module?
Yes, yeah. And that ran in 13 seconds. I says, oh my God, what is going on here? That's bad. And I realized there was one particular loop I hadn't vectorized yet, quote unquote, so I decided to, that was the Euler step. I had forgotten to do that. Vectorized that one, supposed to go faster, it ran even slower. What's going on there? And also here you can see the sort of the notation. You can either loop over the elements, which is the old style notation, or you have the vector notation, and each of these x's and vx's are now arrays. So it turns out that the solution to this whole problem was the length of the array, perhaps not so surprisingly. So what I showed you was for 3 bodies, and it gets progressively good. And you can see actually it gets relatively much better for even 250 particles, and it gets pretty bad for the other ones. So it wasn't too much of a surprise. So that was an example for the n-body system. There's actually quite a nice treatise on this particular website on the various steps how you improve your code for the Laplace equation. All right, so how does that work in reality, at least how I do it? If you write Python code, you actually don't use Python. You don't type the command Python. There is an interactive Python called IPython. It doesn't come with Python. You have to install it separately as a module. But otherwise, you type on the command line on Unix IPython, and the file that I wrote, nbody1.py, you interactively import. And this was a command that I wrote to generate the data. So here's that command that you saw. You create this object from nbody1, the namespace again, the class nbody, and initialize with the data that was created here. And I ran this benchmark, and that's how these numbers all came up. There's a nice function in Python. They all start with percents. If in IPython, if you still like to give commands like ls and cd, you can still do that. You just have to put an exclamation mark in front of it. And that's the way how you run standard Unix commands. But if you want intrinsic commands that are in IPython, there's a few of them, and %time is a useful one. It tells you exactly how much time a particular command took, which is how I did the benchmarks. And there's a command to do some plotting, but we'll show that later in the next talk. So this is my final slide. That's just a little teaser for what's coming up in, later on. All the kinds of plotting that you can now standard do in Python are quite powerful. You can make very composite diagrams. You can make line diagrams embedded with images. A whole widget was built around that. And I think Anatoly is going to show some examples how you can do that in IDL. I want to stop here. There is some, you can read that later, how to install it. There's various ways how to install this, so we won't go on that, and that we'll get to later. So let's go down to the next talk. Let's see if I can fix this. Where would that be? On the desktop? Yeah. Oh, cool. View. Yeah. Slideshow. And then you should take this. Okay, Mark will now tell us about IDL.
Yeah. So actually, I was volunteered to do this. I'm actually not an expert in IDL. I use it now since 3 years.
You told me you were.
Well, 3 years, yeah. So, and actually, I'm also not the person who's most enthusiastic about IDL, but okay, I will try to tell you a bit about it. Okay, so this will be a very personal view. How do I scroll here? How does it work? The next line.
The right arrow.
Yeah, I tried. Doesn't work. Play? Okay, yeah. Okay, it's working. Yeah, sorry. Okay, so yeah, I thought I'd just present some very basic commands since the graphical part will be presented later. So, okay, I guess who of you is actually using IDL? Yeah, that was my guess. So, okay, this is more for the people who never used it, actually. So, a nice thing about IDL is, I mean, once you started it, you have this journal command where you can actually record your session. So you type all your commands. Say here it's just a variable assignment. Then you type journal again, and everything will be written in that file, and then you can run it again later. Another thing of IDL that's very useful is the help, actually. So you just do a question mark and then the command you're interested in. In that case, it's a for. What's also very useful if you run IDL programs, then the ways how to interrupt it, how to stop it, and to run it and to compile it. So you can actually, if you run a larger code, you can always interrupt it with this Control-C, and then you can continue it with .continue. It's not here, but it's a .continue then. And yeah, that's sometimes quite helpful if you want to inspect the variables in your running code and the state of the code. So then you also have, like in Python and all other languages, these control structures. So I mostly use the bold ones here, so not so often the other ones. And one thing you should be aware of if you do comparisons, like in a if then and if else and else case, then for equal you have this EQ, for greater equal you have GE, GT is then greater than, and LG is less equal, and so on. So it's not just the standard symbols for this. I think that comes somewhat from Fortran. And so if you're aware of this, then you can construct whatever you want here in the if. Then you can, of course, also define procedures, like here, and functions. That's also quite useful. And frequently, although not recommended, it's also helpful to use a goto. So it's also available. So especially if you do some kind of debugging and want to jump over a piece of code without commenting it out, you can simply add a goto label. The most important and, from my point of view, the best thing about IDL is how it works with arrays. So this line here actually creates an array of 0, 1, 2, 3 until 4. And then the nice thing is you have this where operator that actually checks conditions on that array and gives you back an index in that array that fulfill this condition. So for example, this where statement returns all entries of this A array where the entries are larger than 2. And then I print A at these indexes, and then I get a 3 and a 4 as expected. And for this where statement, you can also add a comma count, and then it will, in the variable count, write the number of elements it returned. And with n elements of any array, you can get the number of elements in that array. One thing that's can be a bit tricky in the beginning and some common pitfall is the data types in IDL. So if you set a variable a equals this particular number, and you add a 1 and you print a again, then you get this. So the reason is that it's assumed that this is just a simple integer. So what you should do, you can do this number, then add a L, then it's assumed to be a long. If you then add 1, then it's fine. A related issue is that if you do that operation, you want to print the result of 1 over 3. You get a 0, again, because this is rounded and it's assumed to be integers here. So if you want to work this properly, do 1 dot divided by 3 dot. Another nice thing that I use frequently is if you have very large IDL, very large data sets and have to work with them with IDL, then it's sometimes useful to store your variables or arrays temporary because you run out of random access memory. So then there's a very easy way to do this. Instead setting up a complicated I/O, you just have, say, this array A. You do a save A, then it's written in a file on the hard drive in a special IDL format. Then with this command, I actually delete the variable again, so I set it to 0. Then you simply use a restore, and then you have the A again. So that's actually a quite nice thing if you have really to work with larger data sets. You can also get, at any time, the type and the content of variables, just if you use a help, comma A, for example, that's for a string here. And then, as I said, it's best for array operations, actually. So this is, what this whole thing does is actually summing up a series representation of pi. So here I just generate again an array that's the same thing as here, just with more numbers. And that's just some series expansion of pi. So this S will again be an array where all the elements are computed based on k with that formula. And then I print total is just the sum of this array, and that's just pi. So and you can do all kind of operations on arrays. So these are just some examples like median, variance, sort, and histograms, and it all works actually very fast on arrays. The thing, I think I've forgotten to mention this, the thing you should not do, you should never loop over arrays, or you should not use loops at all in IDL, but that's also true for Python. So these loops are usually extremely slow. So you should, whenever possible, use, I mean, I could write this as a loop, just sum over all the S elements, but this would be extremely slow for a large number of elements. So you should always try to avoid loops and use more tricky array operations. Another thing you need is if you make a plot at some point, then you want this plot as a PS file, if it's fine. That looks a bit, I mean, actually I used Gnuplot before I came to IDL, and then this looks quite complicated compared to Gnuplot style. So here you have to set up, you do a setplot PS, then you do a device command to tell him where to write the PS file. Then you give the X size, the Y size, you give the number of pixels, color encapsulated, so you create an EPS here. Then you do your plotting command, and then you have to close it, and then you set setplot X again, so that you have, again, the plotting on the X window. So that's, I mean, quite a lot of stuff to do just for a PS file. So I come briefly to 2D plots. That's also something I was initially not very happy about. So out of the box, all the plots of IDL do not actually look very nice. So, and I, on purpose, did not tune these plots in a nice way. So, for example, you can not read the X and the Y axis here. So this plot was generated just with this command. So I just do generate an array and then just plot the sign. And this thickness just makes the line here a bit thickness, otherwise you wouldn't see it so good. So the point is you can, and here in this plot I use an oplot command to plot a second line on that plot. So the point is you can actually make very nice plots with IDL, but it usually takes some kind of tuning where you want to use the X, Y range commands to set the ranges here. Then if you want to have a square plot where the X and Y scale are the same, then you use isotropic. That's, for example, helpful if you do like in the second exercise of Volker, want to look at the halo, and then you want to have the same scaling in X and Y. Then you can also put multiple plots on the screen or in the PS file. You have to set the p multivariable. And if you want to have, say, Greek letters, for example, or something special in the X and Y label, then it's sometimes helpful to use this tech to IDL command. That's actually a wrapper that creates a string that's then passed to the X and Y label title command, so that you can use tech input and use this here. But I should say that this tool is quite limited. For example, you cannot use tech hat and tech bar. So all the tech commands that put something on above the character cannot be used with that tool. But nevertheless, sometimes it's helpful. So then just a brief thing on image handling. That's actually also something that's very nice with IDL. So here I just load a JPEG file with this read image routine. And then I can easily display it just using TV. So image is essentially a data array. And then you get this. Then you can, so this image has, these are the color entries, RGB. And these are then X, Y coordinates. So what I do here, I set the R and the G to 0. And then plot it, then as expected, you just get the blue contribution. So that's something very nice in IDL. Also, smoothing and histogram operations on images, that works quite nice. For the I/O, I thought it might be interesting to see how to read, for example, gadget data. So maybe if you worked on focus exercises, then you will also need, and you want to use IDL, then you can use something like this to read read the snapshot. So what this does, it declares here some variables so that you have the correct types. For example, the D stands for double. These are then not float, but double precision numbers. And after this, I open here the file. in F77 unformatted. That's where every data block has 4 bytes after and 4 bytes in front of the data block. And then you just do a read U statement, and this one is just the file handle. And then you give them all the things you want to read in. That's essentially the header of the snapshot filing gadget. And then you're more or less done. Then you can extract the number of particles here. That's just this n. And then you can read in the positions and the velocities and the IDs. You have to declare it first. So these are now float arrays. And then you just use, again, this read U to read it in. And this example here, this particular example, actually works with format 1 of Gadget. So as you might know, Gadget has different formats for the output. For example, there's this format 2 that I mostly use. That makes most sense if you write snapshots that have many, many entries. So if you do hydrodynamics and you have lots of additional entries, particle information, then you can specify in that, or you can use a read routine that searches especially for the tags. So in format 2, every data block has its own tag that tells what's written in the data block. And format 3 is actually the HDF5. What I personally do not suggest using it, because for data structure like the snapshots we usually use, the data structure is very flat. So, and HDF5, in my opinion, makes then not much sense. It's more suitable for complicated data sets. So then another thing about IDL is that I think for every problem in IDL there is some solution. But the solution is not always really, I mean, sometimes it looks a bit ugly, the solution. For example, at some point I came above the problem that I wanted to do plots where the y-axis is always in exponential notation, so always 3 times 10 to the 7 or something like this. And apparently to make this work, I found by Googling around this solution. So you had to write a function called exponent that actually does the whole parsing of the construction of the string. And then you use the standard IDL plot command and give it a y-tick format and call this function, and this will automatically then generate a plot where the y-axis is in the correct exponential notation. So if you compare this to other plotting programs like Gnuplot or even the matplotlib extension for Python, that's actually quite complicated. I mean, it's a lot easier in these other languages. But nevertheless, the point is that there's always a solution, but it might not be so elegant. So let me come to the conclusions. So I think the pros of IDL are definitely that it has very powerful data manipulation functions, especially for arrays. That's quite complete out of the box. So if you compare it to Python, to work with Python on large data sets on numerical arrays, then you need lots of additional modules that need to be installed on the system, what's often not the case. That's different with IDL, where most of the tools on the basic operation tools are already available. That has directly to do with the point 3. So my experience is that that IDL is available on most supercomputers, whereas Python is not. So whether you ask them the system administrators to install it or you do it yourself, so nevertheless it takes some work. And especially the modules of Python are usually not available. And actually my reason why I started with IDL, because all the people around me used it. So whether that's a good motivation or not, it's up to you, but especially then you can ask people to help you. The cons are definitely it's not free, so it's quite expensive. There's a free version called GDL. I never tested this, and I'm not sure how it compares to IDL, but at least it exists, so you can try this out maybe. And what my experience is, since given, if you're working at the institute, then usually you have only a restricted number of licenses. So our experience is sometimes that we ran out of license numbers and you couldn't do anything anymore, besides the demo mode that lasts for 7 minutes and nothing more, so that's not very helpful then. Then my impression is also that the online user community for IDL is rather small if you compare it to open source products like Python. It's significantly larger. So if you need help, then it's, from my point of view, easier to search the web for Python-related issues. Then the number of extensions is quite limited. I mean, you have, again, compared to Python, so you have, of course, this Astro library and various other libraries, but if you look for Python modules and extensions, then the number is significantly larger. As I said, the plots are intrinsically not nice, but you can make them nice. Actually, I've seen many, many talks where I can already spot by looking at the plot that they were made by IDL, because I cannot read them. So I think you should, be aware of that fact. And as I said in the last slide, problems can always be solved, but sometimes it requires a bit ugly solution. And I suggest these two links. Actually, the first one is the Astro Library of NASA. And the second, I guess most of the IDL people know this, is the Fanning site where lots of IDL tips and tricks are written down. Also this for the exponential notation I showed. Okay, that's it. Thanks.
Any questions? Then, Matt, let's set up yours, and then just take some questions. Any IDL questions or IDL Python before we go into visualization?
How is the 3D plot?
Sorry?
3D plot?
With,
How is IDL work?
well, I never tried it because I thought it's not so good for it. So, yeah, I never. You can do it, but I have no experience with it. I never played so much with it.
Can I see it?
Yeah.
It's really cool.
Okay.
So I think it would look like particles because the surfaces and can't get up and not
Yep.
Just a quick comment. So if somebody were a new IDL user, I would completely recommend Fanning's Guide to IDL Programming. That's because you really will learn to use it there, like using the online references to learn IDL. His book is one of the most used books of mine in practice. It's very helpful.
All right, let's go on with next.
Hello, my name is Matt Turk. I wrote the YT toolkit, which many of you have been using and some of you have been having problems with. But it's a Python visualization toolkit, massively parallel with blah, blah, blah for ENSO and Orion datasets. I've spent, I guess, a lot of time working with Python for visualization. I developed a toolkit to write my thesis, and so everything that I do is with that toolkit or Python visualization. So I've worked on this stuff a little bit, and I'd like to share with you some things that I've learned. So there are a couple different areas that I want to talk about very briefly. The first of this is two-dimensional visualization. In Python, there are a number of different two-dimensional visualization packages, but I'd like to take a moment just to talk about two of them, the first of which is Matplotlib. Matplotlib was originally written by John Hunter in order to replicate some of the interfaces of MATLAB, and to be able to have a MATLAB work-alike that works with Python that's built on free and open source software. Right here is actually a very simple script that I copied off of the recipe page from Matplotlib, where you just open up your interactive interpreter, you set up an array between 0 and 2 with step size 0.01. You take the sign of it, you plot it, you add some labels, and then you add a grid and you show it. So the glib title is actually not mine, that's from the recipe book. And then you're able to get something out relatively simple, relatively easy, and it's very straightforward to handle. Much like IDL, you can get very nice looking plots, but unfortunately it's very easy to do. So there are other types of plots that one can get besides just regular line plots. Matplotlib recently there's been a great expansion of the development of Matplotlib in order to meet the needs of NASA Goddard. Actually, a guy named Michael Droopboom has been working very hard on things like arbitrary path definitions and alpha blending layers and so forth. So you can do very nice things. You can get histograms relatively easily. These are all off the Matplotlib recipe site, with a regular histogram, tech rendering. Over top of this, a dash line, and then some grids. This is from a new toolkit that's being included in the next version of Matplotlib by a fellow named Jae-Joon Lee, who's at Penn State University, who has actually been retrofitting Matplotlib with a number of astronomical observational utilities. This is an RGB plot where they've taken image data from 3 different filters and then overplotted, and you get a nice RGB blob. You can do spline paths, very, very interesting plotting methods and so forth. Matplotlib also has the ability to do multiple axes, multiple plots on a single axis, as well as quiver. This is actually a plot by Jeff Oishi, where he's used tech rendering for both the ticks along the axis as well as the labels and the legends, and then on top of that a quiver over an image plot. This is some pencil code data. This is actually a plot from my thesis. Matplotlib essentially is basic. You can do simple plots all the way through extraordinarily complex with both a programmatic interface where you manipulate the axes, the individual path elements, and so forth, or very simple interface where you just call it plot, or you just call log, or you just call imshow. It's got tech rendering, and it's great for movies. I'm actually not going to show my movie. We're running a little bit short on time. Another toolkit that I wanted to briefly discuss is called Chaco. This comes with the Nthought Python distribution, but it's developed by Nthought in Austin, Texas. It's free and open source. It's designed for interactive use. This is a function explorer. As you move the cursor, it changes, it takes a line plot along the axis, both x and y, and then moves your ball as your location, and then you get the motion of the curve along the x and y axis out. It's designed for reactive programming, so it's much faster to do interactive GUIs. Interactive rendering, because you describe what the inputs are, and then as the inputs change, it automatically changes the underlying plot. You can do selectable images where you cut different regions. So this is where I've cut out this region, and that's what's been highlighted. The rest is dark on top and bottom in this contour plot. This is another, much like the function explorer, this is a data cube of a brain where along the x and y it cuts out. So you can do relative, and I think this was something like 60 lines of code, including data download and load. But that's about what I wanted to talk about for 2D viz. So the real, the fun part, I guess, would be 3D viz. There are a couple different toolkits available for 3D viz. The most prominent one is Mayavi. This was developed by Prabhu Ramachandran and is now part of the Nthought tool suite, which is essentially a VTK pipeline browser. This is like a mini Paraview written in Python that exposes a full API. Down here is an interactive Python interpreter. Here's your VTK pipeline. And then you can modify all of the different attributes of the VTK objects. It uses a relatively sophisticated wrapper generator so that it generates all of the attributes of all the VTK objects that are part of your pipeline. Right now, Unigrid in Mayavi is awesome. AMR is a little bit trickier. VTK 5.4 is going to have better AMR support for scripting languages. But speaking of VTK, if you want to go down a little bit lower level, VTK is the visualization toolkit written by Kitware Incorporated. I actually have a demo of traded VTK. So what this is something I coded up that accepts AMR data and then builds up a scene graph. You can add marching cubes contours to it. This is the demo effect right here. So you can't see them. If I zoom in, you'll be able to see them. You can edit your operators. All of this is something like 100 lines of code, something like that. So as we move this around, this is the reactive programming where you describe the different inputs to a function, and then as they change, it invalidates the current view and then redraws it on the fly. You can do X planes and Y planes. Anyway, essentially, VTK is via the traded VTK. VTK is a viable and fast way of doing 3D viz in Python. This is just an example. This is actually from something from my thesis work where I've constructed an isocontour of some collapsing star and then colored it by temperature. So you can see these mini shocks inside there. MLab is a much lighter weight interface to the Mayavi TVTK system. You load up, say, a unigrid of data, and then you just say, give me streamlines. You can supply, a couple different parameters to control that. You get widgets automatically that you can drag back and forth. This is another set of pencil data. You can do relatively complex stuff. It's great for 3D functions, simple data, and it's got a very simple, very straightforward interface that's extremely well documented. You can make fairly advanced plots with it. It's got all the different widgets that one would need. S2Plot is it's developed by a university in Australia. It's essentially a 3D version of pgplot. I'm actually the Python wrapper maintainer for S2Plot, and it can do volume rendering, it can do widget plotting and that sort of thing. This is a simple volume rendering. Let me zoom in a little bit. This is a simple volume rendering where I just took, I don't know, 128 cubed and then volume rendered it, tossed on some vectors and added some isocontours. Then there's also, this is a phase plot where I plotted temperature versus density versus velocity. You can do fun stuff like that, and then it's got ability to put on legends and plot and axes and so forth. Anyway, basically what it comes down to with Python is that there are many different choices for both 2D and 3D visualization. They can fit many different needs. And I want to say thank you for letting me share this with you.
Any questions? Oh, yeah.
Did you just do this presentation in the browser?
Yes.
How?
Let's see, did it get cut off? Oh, it's Prezi.com. And that's how the sausage is made.
The concept is called zoomable user interface.
Yes.
And there's a couple of them. It's fascinating. Yeah, go ahead. Yes. The most fun one to do is powers of 10.
That's cool. So you're presenting on IDL?
Yeah.
Are we enemies now?
Why? Actually, another question. How fast is it in 3D? I mean, does it use OpenGL or,
Which one?
well, whatever works in
Prezi.
3D? Yeah. No,
all of those use
the
OpenGL.
Python.
All of those use OpenGL. And you can do raw shader level stuff as well. Mojave is very simple. It's very straightforward. But MLab is probably the gateway drug. That's probably what you want to start with.
What?
Do you need 5 or 10?
5 is great. Well, 10 is better. 5 is great. Yeah.
5 would be great.
Yeah. All right. Okay, so what I want to show you is a few things we do with IDL. So I use IDL not because it's great, but because I use it. It's just for historical reasons. I'm started in astronomy department, and everybody in astronomy uses IDL for reasons that we don't understand. So I use it for mainly two-dimensional plots, and at some point I had to put too many plots on the same page and look at all of the quantities at the same time. So I do these shock simulations, and we have HDF files which have 16 variables in them, and you want to be able to look at all of these variables at the same time. You want to switch the time step, you want to switch the variable, you actually don't know what you're looking for to begin with. So to enable us to do this, we had scripts where you want to change something, you go edit the script, you change the little number, you recompile, you run again, and it became a nightmare. So last November, during the Thanksgiving holiday, I just locked myself in the room and wrote this little interface which allowed you to use GUI where you can command your data with the GUI interface. It wasn't the best Thanksgiving as far as my wife was concerned, but it was, I actually was able to pull this together in about 4 days. So let's hope it works. Okay, here we go. So what it does, it basically looks like an application. So the thing that works underneath this is what's called widgets. So every little piece of user interface here is called a widget, and it has certain properties, and you just write a little code that works with the properties of these widgets. So what this thing does, at first it goes through the directory in which I started it and looks at how many files I have there, and it noticed that I have about 100 files. and then it can read the parameters that were in that files and so forth. So I push this button, replot, and out come 3 random quantities. So let me just push this button, and we'll zoom in. This is a shock simulation, and we're zooming in on a shock. And now I want to actually interact with it. So I pull this slider, and all of the quantities that were in that HDF file are listed there. And I can go and plot some other quantity. This one, not a very interesting one. But basically things like this. And in addition to just doing 2-dimensional graphics, you can do, well, it's all 2-dimensional, but you can plot different kinds of plots. So here's, for instance, a phase space. So it looks at the particles in the directory and plots them together in a phase space. You can plot spectra. And what's cool is that you can actually pull a slider, and it will show you spectra in a particular place in the simulation. So you don't need to hack your script to change the location where you actually want to see the spectrum at, and so forth. So then you can push a button and go back 5 time steps, and another 5 time steps, and so forth. So you can just directly dial which time step you want to look at, and it will do that for you. So all of this is fairly easy to code, and this widget stuff is built into the IDL, and it does require initial time investment, but it did save us a lot of time in the end. So finally, when you have some plot that looks interesting, I just go into the grab, I grab it, and then I can paste it into a document, right? And here is the document I keep, and it's got all sorts of wonderful things plotted in there. And it's a good record of what happened in the run. OK, so that's the IDL widgets. I actually want to talk to the person who said that IDL is great for 3D, because I don't know how you managed to do that. So maybe we should talk after this. OK. It certainly is easy, but the output I got was quite unpresentable for me. But I'm happy to learn how you do that. OK, so another little thing I wanted to show you is another software package I personally use for 3D, because I couldn't make IDL work in 3D. It's called Viz5D, which is a package that was developed by geophysicists for plotting 3-dimensional fields in geophysics. So you can immediately, let's see. Yeah, let's see where it is. Yeah, you can know this is geophysics because there is an arrow that points north. So there's an arrow over there which says M, and it's really hard to get rid of that arrow. But anyways, so what this thing can do is it can interact with 3-dimensional data sets. So over here I have listed all of the data sets in a particular simulation, and I can do simple things like plot slices through 3D data. What's really nice is that it has extremely usable user interface. So if I want to change the color table, I just push one button, and it changes the contrast. And I don't need to click anything else. And then you can write scripts for it. So you use Tcl to write scripting. There's a scripting language included. And with it, you can plot field lines. So this thing went out and traced all the field lines. It found all particular closed field lines in this magnetosphere. And then, so it's fairly interactive because it uses OpenGL, and you can do things like this on your laptop. And it's extremely gratifying to do that. It can also do 3-dimensional rendering. I can try it. It won't look very good because it's a fairly big data set. It's about 160 cells cubed. Other things you can do here, you can plot isosurfaces. So here's, for instance, an isosurface of radius. So here's a sphere, and you can change the radius of that sphere. Here's another sphere, and you can change the radius of that sphere. What's even better, you can color that sphere according to some quantities. So that sphere now has a certain color, and you can play with it like that. So just to finish, yeah, you can plot three-dimensional rendering, and then you can try to change the opacity of various quantities. So what I'm changing now is the opacity of that 3D data. And what? I'm pressing Shift down. And that white line is the indication of the transparency of the 3D data. And then, so now you see something starting to show up. And it becomes less responsive, of course, once you have all that on your screen. But in principle, it works. So yeah, there, it's rotated. So the thing I like about this is it's very, very easy to use. It's very GUI interactive. The downside is that you have to convert your data into some particular format that it prefers. It's actually a very nice format because it substitutes all your real or float numbers and makes them integers in the color table of 256 integers. That way, because you never can see the floating point with your eye. All you really see is color. So it's enough to discretize everything in color table. That makes your data much, much, much smaller. So this 160 cube data set could fit in a fairly small memory. And the downside is that there isn't much development going on with this tool anymore for some reason. So after 2003, it hasn't been there weren't many releases after that. So it's either a bad sign or it means it's perfect. So there is nothing else that can be done. So there. So I'll stop here. OK. Who's next?
Derek is going to show something about Pavray, right? And Chris is there too, right? We started a few minutes late, and I hope we're almost out of time, but I hope we can handle this a few more minutes. So there's Derek, and then Chris, and then we're done. Yes, I forgot. You're on there.
Somebody left their dongle up here. Okay. Yeah.
Are there any other programs that we've seen listed that we're going to discuss that we think should be worthwhile mentioning? Somebody said, I use MATLAB, but I don't understand it on the stage. Tell me about it. Any other packages that you would at least like to know the name of for others? ParaView. There was somebody who was using ParaView here, I thought.
I use some ParaView. I'm just getting to know it. So yes, it's similar to some of the other things that you showed. Actually, the Maya with, or what was it called, Maya View, I hadn't seen before, but it's sort of a more powerful Maya View from my perspective. Has a bit of a learning curve, but once you get to know it, it's very powerful. It's in lots of common formats, including BTK, and it's supposed to be able to do both analysis and rendering in parallel. So if you set things up, you can do rendering on multiple GPUs and then combine images. Yeah.
All right, Derek.
Should I go? OK. Real quick, Pavray, I've showed you some examples of using this in my talk. It's available for free. It's a ray tracer, which means you basically give it a scene, a camera location, lights, objects that you want to visualize, and then it'll do a nice rendering for you. And it can get arbitrarily complex. This is entirely rendered inside Pavray. And this is titled Bad Tree because the reflection is not the same as the actual object. If you want to go to the Pavre Hall of Fame, you'll see some amazing images. Pavre.org is the place to go. It's very simple. What I like about it is that I can take my own code and output my data in Pavre readable form, because it's very simple. You basically, so here's an example, put a camera here, look in this direction, put a light source there. Color 1 means white in this case. I'm going to put a sphere down of radius 2 at the origin. I'm going to color it red, green, and blue. You don't have to use RGBs. You can use red and stuff like that, but this is the simplest way to do it without using include files. And then we added this extra finish here to put a little thong on it and make it look nice and three-dimensional. And last night I added some new functionality to Picadilgraph to do a oscillating wall. And I'm going to drop a bunch of metallic balls into it. This is all rendered using Pavre. And here's the movie. And there actually are serious applications of this. I like to study the Brazil nut effect in low gravity. Do rocks on the surfaces of asteroids migrate to the surface? That sort of thing. So there are actually applications for this. But really cool movies. This was very simple to do. Okay? And it took 6 CPU hours to render and 1 minute to do the simulation. So the rendering time is the killer here. You can actually do Pavre ray tracing in parallel. I haven't bothered with that, but if you want to get really serious. Peter asked me to look at Blender, which is another public domain piece of software, blender.org. I haven't played with it myself. It seems to be more oriented towards creatures, like building good human faces, bodies. This was entirely rendered inside Blender. Very good for Hollywood-style movies. It has the advantage of a graphical user interface. Pavre is all done with scripts. It's not obvious if it's going to be easy to render scientific data inside Blender. I didn't look into that, but it does support Python scripts. So maybe there's a way to do that, and you could visualize your stuff. And lastly, real quick, Second Life. Any Second Life users here? Nobody? Wow. This is me in Second Life giving a presentation shown here. These are my slides. This is my laser pointer right there. I have animations showing on that wall. These are the people in attendance. That's Peter, who's asleep at the table. Okay. Worked really well. I had a headset. I was at home on my laptop, and I just gave the entire talk. It's really cool. And the other thing about Second Life is that you can actually do visualizations. And there's an entire community looking at trying to do, to look at M-body simulations in an interactive virtual world environment. So very quickly, this is me. I've got a very clever name, my first name spelled backwards. Okay. Hello. I don't normally wear a tie. And I'm going to walk towards this area over here, where you see someone has constructed what I think is an HR diagram in 3 dimensions. And you can visualize it like that. Whoops. Okay, so this is just sitting out there inside Second Life. There's an entire, somebody has put together a package that allows you to upload data into an object, which you can then res into the world and visualize your data in 3 dimensions. I could go on about Second Life ad nauseum. If you're interested, please see me offline. I'll stop there.
Thanks, Derek.
You bet.
Are you hiring postdocs?
What's that?
Are you hiring postdocs?
Am I hiring? Just hired one, sorry.
Do you accept
Oh, right, yeah.
One more little one.
So I'm going to talk about Visit. Visit is a visualization package, all GUI run, very, very nice, very, very easy to use. How many people are using Visit, by the way? So just a few, yes. You Yeah, more people probably should be using it. So Visit is a free open source visualization package developed and maintained by LLNL, people at LLNL, and they're still working on it. New versions come out every few months, it seems like. There's a great forum for it where you can talk right with the developers and they can fix it for you very quickly. I've had them address issues that I've had before, or at least give me fixes around it very, very quickly, so that's nice. Does 1D, 2D, and 3D, but I crossed out 1D because there's much better things to do 1D for. This really is not for 1D. This is more for really pretty 2D and 3D stuff, and also does a ton of great stuff with animations. Supports lots and lots of data types, both input and output. Just about anything can be easily manipulated if it's not already natively supported to work in there. It has an actual usable, really user-friendly GUI. User interface, supports scripting, so you can script in Python, so you don't actually even have to use the GUI if you don't want to. You can script everything in Python and have it run in the background for you. Or you can even script in Python while using the GUI and watch it, and then as your script crashes, you can quickly change it while the GUI is still there. Very usable. Runs in Linux, PC, or Mac, so there's installs for all of those, and it's probably the easiest install I've had. You download your distribution, you download an installation script. You don't even have to unzip the actual file. The installation script will unzip the file for you. You just run the script. It does it all for you. It's very, very, very easy. It can be driven externally or remotely. So if you have a big machine somewhere that actually has all your data on it and is running the visualization, basically what you can do is you can pull up Visit on your machine, and then you can type in that host address for that machine that has Visit running on it. And it just basically, it'll do the rendering on your side, but it'll do all the data manipulation on the server side. Also, it runs in parallel. And so this is really, really cool. There aren't too many scientific visualization software out there that do this, but they have the parallel distributions available. Also, if you have time on Ranger or any of the Texas machines, you'll actually also get some time, through TeraGrid, you'll get time on a cluster called Spur. And it's a visualization cluster with dedicated machines to using Visit in parallel. So it's really cool. You can get 16 processors, so you're doing your visualization 16 times as fast. Works very, very, very well. So that's really cool. And so some of you may already have time on this machine and it's just sitting there and you're not using it. So like I said, it supports a lot of input data types, and anything that's based off of HDF5, it can sort of read. It has a generic reader that will sometimes read it. If it's not able to read it, they actually have a whole document that tells you how you can actually get your data in there. So if you're using some sort of off-the-wall data type, it can still get it in there for you. So like I said, it uses a GUI interface. Basically, so this is the main interface here. So here's where you pick your files, and it's really good about maintaining databases. So if it sees a bunch of files that have similar names, it calls it a database, and it says, okay, well, this is probably, such and such 000 is time step 0, 001 is time step 1. And it'll let you step through those time steps with these controls here. The way you plot something is you just choose your plot type here, you click on plots, and you pick which type of plot you want. A very common one is like pseudo-color, streamlines, surface. It'll even do some volume rendering, although that's tricky to get it to look good. So you select your plot type, and then you select your variable. It'll look through your HDF data and find all of your variables, or you can define your own variables. Then there's also these things called operators. So there's another button here that says operators, and that lets you do all the normal stuff that you're used to doing. Anything from you can take a slice out of this and take a 3D data and slice it into 2D data. Here I've cut out a sphere on this piece of data here, and you can just do all sorts of great visualization things. You can plot multiple plots on top of each other, multiple variables, set different levels of transparency relatively easily. So it also has, I think I deleted some text here, so it also has a line out tool, so you can draw a line and it'll give you a graph of that for you. It supports, like I said, user-defined variables, so if you've got a bunch of variables and you want to do some math on it and plot it, you can do all of that within Visit. You don't need to do anything outside of it. It has a query tool, so if you want to quickly find that one data point that's screwed up, that's way beyond everything else, you can do a search for the max or the min or all sorts of things on there. It's very powerful for that. And then I'll show you some of the pretty pictures I made real quick. So this is 2D, got a mesh, you've got vectors. Here's 3D. I've plotted the mesh with some transparency. I've plotted an accretion disk with various contour levels, and then another plot showing the jets, another contour with some transparency. Again, more contour plots here. This is showing the processor distribution. This is showing half the mesh and contours of an accretion disk. Again, just various, different plots, 2D, 3D. Here again, just showing you different contour plots with different levels of transparency. As you can see here, it supports multiple levels of refinement. So if you have a code that uses AMR or uses multiple grids on it, it can figure all of that out for you. And so that's what this is done here, is showing that. Again, another just plot here with some of it cut away. It supports streamlines. Those are really tricky to get working, but when you do, you can get some really pretty stuff and really see these magnetic fields, and it's really powerful. It's just kind of hard to use. More 2D plots. Here's another great 3D contour, and then these are all the vectors, and you can color the vectors by a variable, as well as having them, or you can size them by a variable. And then really quickly, I guess I can show some movies here. So this is an accretion disk, and what you're seeing is the formation of the magnetic field lines, and then this is showing the unbound material here. What you can see in this video down here is it actually supports red, blue 3D and lots of other 3D types. So if you have 3D glasses, this is really cool. You see the jet blowing up in your face. It's really fun. And then this is just several levels of contours with transparencies of an accretion disk again. And that is about it. So questions on that? Yeah. Used what? No, I don't think so. Yeah, I don't know. I'm using it. Mm-hmm. Yes.
So a quick question. So one of the nice features of Visit is that the compute engine can reside where your data is, and then it can pipeline to your desktop.
Right. Right.
Have you experimented with that mode, and is that pipeline efficient?
Yes, I've played around with that some. It's a little tricky to get set up, but yes, it is very fast if you can get it to work. But usually, if I'm doing remote machine stuff, like right now, I usually use the remote Spur cluster, the Texas Spur cluster, and that I'll just use VNC. That's what they recommend doing, and actually running Visit there. But yeah, I've done that pipeline thing. If you can get it to work, it's very, very fast. But yeah.
So does VNC actually transmit update the...
Yeah. Sorry, it's unplugged now, but yeah, it does. Right now, I've got a VNC. Yeah, opens and transmits it very fast. So yeah, but yeah, that's what I'm doing right now.
Do you need a special VNC that's enabled with OpenGL?
I don't know. The default one, so I'm using Type VNC for Windows, and that works fine for it. And I know on a few of the Mac ones, it works fine. Yeah. Yeah. So I'm not using anything special, I don't think.
All right, and then we have one more very short contribution. Heino had a really cute animation. He's going back to basics when a lot of the rendering you see is done by OpenGL, the basic graphics that allows you to do it very fast. And I believe I saw one of your pictures that you were able to do it on an iPhone now. So we'll see a short presentation on that, and then we're done. We can go straight to the pool party.
Yep, so it's me between you and the pizza. So if you don't like packages and you want to do it yourself, then OpenGL is the way to do it. It's very simple to use. It's pre-installed basically on most of the systems. For example, on the Mac, if you have Xcode installed, then OpenGL is there at all. You don't need to install any libraries at all. And I'm just going to show you a very simple example. So I uploaded those to the Google Groups web pages, so you can just download it and play with it if you want to. So there are about 20 lines of code that do everything for you. What it does, first of all, you define a function called display that does your drawing. You have to clear the buffer before you draw anything. You have two buffers. You draw into the buffer, and once you've done the drawing, you swap the buffers so the user only sees the finished picture. That's why we have to clear the buffer first of the display function. At the end, we swap the buffers. And then in between, I'm just plotting some random data here in this example. So I'm choosing a color.
I can set the transparency. I can move it to a position in my 3D space with the translate function. And I can also display more complex objects like a sphere without anything. And then you have to do some initialization in the main routine, but it's basically very simple, and you can just copy and paste always the same code. Okay, so let's compile this. Oops. You see, I don't have to install any libraries. The frameworks OpenGL include are already installed. And then you can run it. And it's on my other screen. It disappeared. Yeah. Sorry.
It's a demo.
It's a demo, yeah. If you look quick enough, it works. Yeah, that's the demo effect. Okay, so that was a very simple example. And if you write not 20 lines of code, but let's say 100 lines of code, you can do something like this. It's really not more than 100 or maybe 200 lines of code. That's my code that I use for normal research. So that's a gravity calculation. It's a tree code. And yeah, it shows you particles. And that's calculating real time, both the simulation and the visualization. So you can actually really debug your visualization in real time by just looking at what's going on. For example, you can print you can display the grid of the gravity tree code, so you see how it works. And it's also fully 3D, and interaction with mouse and so on is very straightforward to include. So yeah, can do fancy stuff if you want to. Yeah, all in a few hundred lines of code. And now, as Peter already mentioned, OpenGL is very portable, and you can use it basically on any device you want to. So within an hour or so, you can port your code to, for example, the iPhone. And it's exactly the same code, because the iPhone also uses OpenGL, and yeah, you can do science with the iPhone. Okay, that's all. Thank you.
Well, we had hoped to spend another 10 minutes on discussion. If somebody wants to say something, I'm happy to entertain, but the pool party will be in 10 minutes, and it's a 9-minute walk. So 1 minute for questions. Any comments in general?
I wanted to mention that the 3D stuff that I showed is all glasses enabled. The 3D stuff that I showed is all 3D glasses enabled.
Thanks for all the contributions. I will collect, make sure that what we've all presented and what is available as a PDF will be distributed through the wiki and the website. Thanks. See you at the pool party.